This is Computer Programming 1 from the University of Washington. Welcome back. Today in Lecture 2, we'll be going right into the technical content of this course as we talk about problems, algorithms, and programs. As you may be aware, programming a computer involves a great amount of detail. We'll have plenty of time later in this course to get to many of those details. But programming also involves higher level concepts and problem-solving skills. I'd like to focus on that today. Later on, we'll see details that will help us carry out these higher level problem-solving strategies. So we'll talk today about what problems might be solvable by computers, what algorithms are, and what programs are. We'll talk about a general approach to solving problems with computers and discuss how our solutions can be turned into code that a CPU can actually execute. We'll focus today on these large ideas. To start with, computer programming is primarily a matter of using a computer to solve a problem. That might be one definition of programming, problem solving through computers. Now, not all problems that we refer to by that name in everyday use might be amenable to solution by computer. The problem of traffic jams during rush hour, for example, probably can't be solved by writing a C program. And the same goes for problems like world peace or world hunger. Part of the art of programming is being able to recognize which problems are suitable for solutions. In general, a problem that a computer can solve has to be one for which you, as a programmer, can come up with an algorithm. An algorithm is a sequence of precise steps which will lead to the solution of the problem. If you can't come up with the algorithm or sequence of steps, then you can't use a computer to solve the problem. These steps have to be quite precise, and they have to be mechanical in the sense that they'll be carried out by a machine, the computer, once the programming is done, rather than by a human being. The notion of an algorithm is a fundamental one, and perhaps it's what distinguishes computer science from other fields of science and engineering. Certainly, algorithms are used in many other fields, but nowhere except in computer science is the algorithm itself, the notion, nature, characteristics, capabilities of algorithms, the central area of study. If you can come up with an algorithm, then the next step is to turn that algorithm into a computer program. A lot of this course will be about that process, taking the algorithm and turning it into a program that can be executed. Now, we express the algorithms using what we call a programming language. This is a special notation that we will be able to translate into a form that the CPU itself will be able to execute. Our course focuses on the C language. There are many other programming languages. You might have heard of some of them. C++, Java, both of which are quite closely related to C and derived from it. Others, Fortran Basic, you may have experience with. Let's compare programming to another kind of algorithmic activity that we're familiar with from everyday life, namely cooking. So let's take a typical problem. You're hungry, you need to eat something. Fudge brownies sounds really good. So here's the problem. You want to make some fudge brownies. Okay? That corresponds to the statement of the problem. The goal, make fudge brownies. What's the algorithm? Well, in cooking we call that a recipe. A recipe is something like open 2 bags of chocolate chips, put them in a bowl, add 2 tablespoons of flour, and stir them together and bake in the oven for 3 hours, or whatever the algorithm is. You may know more about cooking than I do. Okay. That's the algorithm, though, the step-by-step recipe that tells what things to do in what order. Now, is that quite like a program? Well, not quite. When we write a program, we'll be giving it to a particular computer to execute, and we have to write it in a language and a notation that the computer understands. Just like our recipe has to be written in a language that the cook understands. Okay? So I may know the steps to go through and the ingredients, but I've got to say that in English, in Russian or Latvian or whatever the language of the cook is. I've got to use the right terminology, the right operations, and do everything in exactly the right order, or I'm not going to end up with fudge brownies. Okay? And I'll still be hungry. I won't have solved my problem. Here is a procedure that many people find useful as a general strategy for solving problems with a computer. The first step may be obvious, but it's worth stating, is to specify what the problem is. Now, although that's obvious, it's often hard to do. Problems that you're given to solve by a client, a customer, a teacher, are sometimes vague and may take a considerable amount of, the next step in the process, analysis. Studying the problem, understanding what it really means, what's really sought, learning more about it, as much as you can find out about it. Eventually, from that study, you hope you can design an algorithm, the step-by-step procedure for designing the problem, designing the solution to the problem. Once you've got the algorithm firmly in mind, you can then implement the algorithm. This means writing the program. Now, it's really only at this stage that you need a knowledge of the programming language. So you could do the problem specification, the analysis, the design, without knowing whether you were going to use C or Java or Fortran. And then, at the implementation stage, begin translating that analysis and algorithm into the programming language your computer will use. Are you done yet? Well, it would be nice if that was the last step, but it's very easy to make mistakes somewhere in this process. So the program that you write has to be tested, verified, and in doing so, you may find out it doesn't work exactly as you planned it to. Where is the mistake? Well, it might be in the programming, but you may find out it was some oversight in the design. Or maybe you have to go back even a further level. Maybe the analysis was wrong, or the problem was stated wrong, or you misunderstood what the person who gave you the problem wanted. All of these things will require reanalysis, redesigning, and then fixing the problem, or hopefully fixing the problem in the program and trying again. So an iterative process involving all of these steps. Let's take a simple problem and apply this procedure to it. Okay? Here's the problem. Is a given number even or odd? Sounds simple? Yes, it is simple. Why such a simple problem? It may seem unrealistically simple to spend time on in a course. But actually, it's not so far removed from real-life problems that you might want to solve. If you have a payroll system and you print checks every other week, you have to determine whether this is a payroll week or not. What about the problem of determining whether a year is a leap year? That has a similar flavor to it. Beyond that, in a course like this, where slides are used to present information, it is difficult to completely solve and present complicated problems. That's one of the reasons, by the way, that we recommend you look into the textbook for this course or another textbook or another book on this subject so that you can see larger, more realistic, and more interesting examples. But for now, this example will serve us well. It will allow us to go through all the steps recommended for problem solving, and when we're done, we'll come up with a complete solution to the problem, including code. So, what would I say the first step was? State the problem. Apparently, I've done that already, and so I can go on to the analysis. And here, you may start thinking about, what's really meant? What numbers are allowed? Is a negative number one I need to get an answer for? What about a fractional number, like 10.3? Does that even make sense to ask the question for even or odd? You have to ask yourself these questions, or perhaps ask the client or teacher who gave you the problem. where does this number come from? Is this one number that's fixed forever? You have to think about that before you can write an algorithm for the program. And then there's a more basic question about what even and odd mean. These are mathematical concepts. Most people will remember this from their school mathematics, but if you're not sure, this would be the time to go back and look up and remind yourself what those concepts are. I have had even college-level students with 12 years of school mathematics behind them not be sure whether 0 is an even or odd number. Okay, so it is possible to have doubts in your minds about these things. And the analysis phase is when it makes sense to figure out what is really meant. Finally, the program says determine the answer, but how do you report that answer? Do you want the computer to light up a billboard or speak a word? How is the answer to be reported? You have to decide on that too. This analysis might lead you to restate the problem in more precise terms. So let's try to do that now. Let me restate the problem I'm really going to solve as this. Given an integer number, okay, so now I've pinned down the kind of number it's going to be. It's going to be an integer, number without decimal points, typed in from the keyboard. So it's not built in. It isn't sent from a satellite, okay, or some other obscure method. It's going to be typed in. If it is even, write even on the screen. So now we're specifying how the answer is to be reported. And if it's odd, we're going to write odd on the screen. So now we have a much more precise definition of what the problem is going to be, and we can proceed to try to think about an algorithm. So here's one. Let me suggest this one. Read in the number. That seems a logical first step. Okay. Divide the number by 2. Observe what the remainder is. If the remainder is 0, write even. Otherwise, write odd. Now, to determine if this algorithm is correct, you would have to compare this with your knowledge of the mathematical concept of even and odd. Okay, and I think it's right. I think this algorithm ought to work, okay, based on what I understand of the problem and what even and odd mean. Okay. Example. Here's a number. I think if you put the commas in, you'll find this is 23 trillion something or other. Okay, so you whip out your pocket calculator and try out this algorithm. Punch in that number if you have enough display digits on the screen. Divide it by 2. See what the remainder is. Hopefully your calculator tells you that. Or maybe you can do this by hand in the long division algorithm. If the remainder is 0, write even. Otherwise, write odd. Well, what is the answer going to be? I think you're going to tell me that the answer is odd. Now, how did you do that? Did you have time to do that division right now? My guess is you didn't. My guess is you actually used a different algorithm. That's what I did mentally when I worked this problem. Here's the other algorithm that a human being is more likely to use. Take the number and ignore everything about it except the rightmost digit. Okay? If that's a 2, 4, 6, 8, or 0, write even. Otherwise, write odd. Here we have two different algorithms. Either one would give us a correct answer. We need to pick one of them and use that as a basis for our program. So in the program I'll show you, I've picked the first one. Okay. Turns out just to be a little simpler to program, but I also could have used the second one. So maybe it's easier for the human to use the second one. Sometimes computers do things in ways that aren't necessarily natural for humans. It's something with experience programmers begin to recognize. So we've got an algorithm. Well, we had two actually, and we picked one. Now we'd like to move on and write the C program. What do we need to do that? Well, we'll have to learn more about C. But maybe we should step back at this point and discuss what a program really is. And to do that, we've got to go back even one more step and talk about what a computer is. Let's spend a few minutes doing that now. Here's a diagram. Now this may not look much like the computer sitting on your desktop or the one in your wristwatch or your VCR. But believe it or not, most computers have an architecture or an organization similar to this one. They have visible parts, they have screens and keyboards and mouse pads, wrist displays, and so forth. But actually, those parts aren't what make that a computer. The real heart of the computer is buried deep inside. You seldom see it unless you're the kind of person who likes to unscrew things and look inside. The two parts that really make a computer are deep inside, and they're the central processing unit and the main memory. Central processing unit is the brains of the computer. Sometimes we abbreviate the CPU or just call it the processor. What it does is very simple. It executes instructions one at a time. These are normally extremely simple instructions, like comparing two numbers or adding two numbers, some very simple operation. And as it does this, it's able to manipulate, look at, and change values in the main memory. Now, this seems awfully simple, and you might wonder how a computer could do so many fanciful and wonderful things with such a simple basic operation. Yet it can. Part of its secret to being able to do wonderful things is it can do these simple operations very, very fast, much faster than a human being can do them. And so we can put together lots and lots of these instructions, and as we do that, the computer is doing more and more complicated and interesting things. But at its heart, and this is important to keep in mind, all the CPU is doing is one instruction at a time, one after the other. So for the computer to do anything useful, we have to give it this sequence of instructions. And that is the definition of a program. So here we have it. Our main definition of the course, perhaps. A computer program is a sequence of instructions. Sometimes we use the word software. Sometimes we use the word code to refer to these sequences of instructions. Without these programs, the computer is useless hardware. It can't do anything useful or interesting. Complicated programs may have millions of instructions. Several years ago, I was told that Excel had 5 million instructions in it. And by this time, I'm sure it's many more than 5 million. Operating systems contain even more millions of instructions and are getting bigger and more complicated all the time. Well, we know what a program is now, so you can guess what the definition of a programmer is. It's someone who is able to create these sequence of instructions to do something interesting on a computer. Well, CPU is one part of this organization. The other part was memory. The memory is a collection of locations. It might be quite large. You have a computer at home. How much memory does it have? Maybe when you bought it, it had 96 gigabytes. Probably that's not the main memory. That's probably hard disk drive. On the other hand, if you were told it had 96 megabytes, that probably refers to the main memory, 96 million bytes of storage. Each byte in the storage can hold one small item of data. Now, fortunately, we seldom have to worry about the memory locations, because in programming languages we refer to them as variables, and we can give them names. So within the program, we'll have variables. Each one does correspond to some memory location or memory locations. But in our programs, we'll only have to know their names. And our variables will also have types, something about the sort of data they can contain. We'll say a lot more about this in the next lecture, but types might be things like numbers, might be integer numbers. They might be floating point or so-called double values. They might be characters, like individual symbols that would be printed or displayed. So with this background in mind, and knowing what a program is, let's go back to our algorithm and translate it into C. Okay. You remember the algorithm. I've restated it here with just a little bit more detail to refresh our memories. We're going to ask the user to enter a number, read the number in, and we're going to call it num. So here I've introduced the notion of a variable, location in memory where I'll store this value. We'll divide this variable by 2 and call the remainder rem, another variable. If rem is 0, I'll write even, otherwise I'll write odd. Okay. So I don't have a program yet. I have an algorithm that does contain some programming concepts, but it's not yet in a form that the computer can understand. It isn't in a computer programming language yet. Now, I'm just about to show you a real C program to do this. Now, don't panic when you see it. It's going to contain all kinds of little details that I'm not going to try to explain today. It isn't the point today. We will get into that soon enough in the next couple of lectures. Okay, here you go. Here's the first part of the program. Won't fit on one slide, so I had to break it into 2. Take a quick look at that, and I will go on show you the remainder of the program. And again, don't panic. If you have a copy of this printed off, you can look at it in more detail later, or perhaps come back to it later in the course after we've talked about the concepts that it shows. Instead of going through it line by line, I would like to highlight a few features of the program and its operation. First of all, when I run the program, it doesn't look anything like the program itself. Okay. I see only on the screen the statements that correspond to instructions I've given to the computer to display things. So when I run the program, I will get a message that says, please enter a number. The 17 is not printed by the program. That was typed in by a user operating the program. Okay, it'll go off, and then seemingly instantaneously, the program will come back and display that word odd. Then the program finishes. The last line you see there, press any key to continue, is not from our program. It's from the operating system that ran this program for us. Let's look at the program text a little bit. You see that some of the text is enclosed between the slash asterisk and then followed later on, you see, by a asterisk slash. These are comments. They don't affect the operation of the program in any way. They're there for you to help you remember what you did with the program, help you document the algorithm, the decisions that you made, the way the program is organized, and so forth. They help you remember that. My experience is that if I write a program and then don't look at it for a week or two, when I come back to it, I'll be completely mystified by what it was supposed to do. I can't remember those decisions unless I put comments in to help. Comments are also important for other people who read your program, such as bosses, co-workers, your successor in the job that you quit after writing the program to go on to a better job. And for some of you, this is very important, the people grading the program. You may find that they consider the comments very important, so take their opinion seriously. Here's something else we can highlight. Remember that variables are named locations in memory. This program uses 2 variables, and the yellow box shows where they are declared, that is, or first defined in the program. Something else that's important in programs are statements. Statements correspond to operations that the CPU will perform one after another. The statements in yellow here will be performed in the order they're shown from first to last. We'll study quite a few different statement types as we go through the course. The first one will come in the next lecture. Finally, something we'll spend a lot of time talking about in this course are functions. Now, functions are sets of statements that are not directly with your code, but may be written somewhere else or even written by someone else that you can call upon to perform operations for you. Using functions is a very important part of learning how to program, and so this is why we'll spend a lot of time on it starting a little later in this course. There are a few places that weren't highlighted by any of the other preceding slides. Let's just call these boilerplate for now. They're things we won't be explaining very soon. For now, they're things that have to be there in every C program that you write. Eventually, though, we will be able to explain why they're there and what they do for you. Are we done? Do we have a program that we can run? Well, not quite. Not quite. The problem is that the CPU doesn't actually understand C. And it doesn't understand Fortran, it doesn't understand Java. All it understands is an internal machine language, a language of ones and zeros. In fact, this language varies with the type of machine. IBM compatible Intel PCs understand one language, Macintoshes understand a language, Suns understand a different language. So we're not done once we've written a C program. We're going to have to translate that C program into something the CPU will be able to handle. Now, to do that, we don't have to do the translation manually. Programs have already been developed to do that. As you program, you'll use these tools. One of them is a compiler. This is the program that takes your C statements, we call this the source program, and does the primary translation into the machine language of the CPU. Now, that's not quite enough because of the functions I mentioned earlier. Those functions also have to be combined with your program, and they may not be physically present at the time your program is compiled. So another program called the linker will take all of these ones and zeros and put them together and come up with an executable, that is a file that the CPU can execute. On Windows systems, these have extensions of .exe. Now, most people will not be very aware of the compiler and linker running. There will be a development environment, and perhaps you will just press a button, build perhaps, and that will cause the compiler and the linker to execute automatically. Here's a picture of what this might look like. Let's not focus on all the boxes, but look with me for the box labeled .c file. Okay, it's a little hard to spot there on the left. That's your program. That's the C language program that you have written. It expresses your algorithm in the C language. Okay. Once you've written that, you'll send it to the compiler some way or other, maybe pressing the build button. The compiler will then create the ones and zeros file. You can see right in the middle there. It's a bit faint. Okay. If there are no errors in that process, then the linker will take that and will combine it with programs from other sources, such as libraries, and produce the circle on the right-hand side. This is the executable program that can be used by the CPU, and it can also be used by other tools, such as debuggers, that we won't talk about at this time. Are we done yet in our high-level viewpoint? Well, unfortunately, no, not necessarily. There's still plenty that could go wrong. Okay? One of the things that you find out very quickly as you begin programming is that things are rarely perfect the first time you try them. Even though you spent a lot of time analyzing the program, you have a wonderful algorithm, and you've very carefully written the C program following, you think, every rule that exists, still there may be errors. Now, some of these errors may be caught by the compiler. And if the compiler can catch the errors, that's a good thing, because it means you know that they're there and you can correct them. Although the compiler doesn't always explain very well why the errors are there that it catches, but at least you know something's wrong. So you get rid of all the errors that the compiler can see, and the linker doesn't tell you there are any. Are you done now? No, you're still not done, because there's another class of errors that might still be present. These are errors in your logic or thinking or in your algorithm. Okay? So you may have an algorithm that you have translated into C code perfectly, but the algorithm itself has a problem. It has a step missing or a step that's incorrect. Okay? Maybe that incorrect algorithm is because you didn't analyze the problem, or because maybe it's not your fault at all. Maybe it's the person who gave you the problem stated it wrong. But there are all sorts of opportunities for errors. One of the problems facing people who develop large systems is finding and removing these errors. This is a very significant challenge, and it consumes a great deal of the resources of professional software organizations. Sometimes errors may not be visible or may not be detectable for a long time after the program has been in operation, apparently error-free. Okay? So 2 months after the client happily accepted the program, the phone rings at 3 a.m. The program just crashed. It just printed even when it should have printed odd, and it never did that before. Well, you're not sure what's wrong, but you do know that your good night's sleep has been ruined. Let's put some terminology to these categories of errors because we'll encounter them again and we want to have good, precise terms for things like this. Syntax refers to the required form of the program. Certain rules for punctuation, certain words have to be spelled certain ways, and so forth. These kinds of syntactic problems will be caught by the C compiler, always. You can count on that. Now, it may not tell you very informatively what the problem is, but a syntax error, by definition, actually, is one that the compiler can detect and report. The other kind of bugs, the logic bugs, the ones that get you out of bed at 3 in the morning, the C compiler cannot catch these. Okay? This is a very unfortunate situation. It's a fact of life, though, that you'll have to learn to accept. Bugs can be very, very difficult to find. There are commercial software products used by millions of people, I won't even mention their names, which are known to have thousands of bugs even when they're released. Okay? Thousands of bugs. Why aren't they all fixed? It turns out that finding and fixing bugs is an extremely difficult problem. It may be as difficult as solving or designing the problem in the first place. Of course, manufacturers now take a slightly different tack. They don't refer to these as bugs or errors anymore. We now have a wonderful euphemism for them. They are issues. Love that term. You know, you ought to try this for yourself. Don't just take my word for it. You could go ahead and type this program in. Now, since you don't know the rules for C yet, you should be very careful about the spacing and the spelling and so forth. Later on, you'll begin to see where you can relax this. But for right now, you should just type in extremely carefully. And if you don't make any mistakes, and there were no typos on the slides, well, you will have a program that operates as I showed in the example. Okay? If you get it operating correctly, here's a fun little thing to do. Go back and deliberately introduce an error, just to see what happens. Okay? See if that causes a syntax error. If it is, how does the compiler report it? Does it correspond to the change that you know you made? Or if it's not a syntax error, does it show up in some other way? Does it cause the program to give the wrong answer? Experiment and see what happens. That can be a fun way to learn things. In fact, computer science is in many ways an experimental science. Okay, we have really covered a lot of material today. Lots of new concepts, lots of big, important concepts. Concepts as big as the whole field of computer science itself, like what is an algorithm, what is a program. We've looked at what a computer is and how it's organized. We've seen, with no detail, some basic components of C programs, such as comments, declarations, statements, functions, and so forth. We've talked a little about this process by which compilers and linkers prepare our program for execution. We've talked about the nature and difficulty of bugs. We've had a lot of terminology, too, and that's going to continue to be the case in this course. We will introduce quite a bit of terminology each time we have a new lecture. So you can see what the plan will be for the rest of the course. We're going to be filling in the details and seeing ever better ways of solving problems using a computer through programming. So please get started. Try this stuff out. Go on to the textbook, begin reading, and please join me again next time as we get into nitty-gritty details on variables, values, and types. Thank you.